Alright, let's take a look at the first fundamental theorem of calculus. And it says, let f be a continuous on closed interval ab, and if f is an antiderivative of the function f on the closed interval ab, then the definite integral from a to b, f of x dx, is defined to be, or is equal to, the antiderivative evaluated at b minus the antiderivative evaluated at a. And so we're going to take a look at the proof. So we're going to go ahead and partition the interval AB. So x naught will be a, and then we'll partition it into n plus 1. It's going to be n intervals, or n plus 1 points, where the x naught is a and the xn is b. So we're just going to partition that up. And from that, we're going to make an observation or a note here that f of b minus f of a is going to be equal to f of xn, which is f of b, minus f of xn minus 1, okay, plus f of xn minus 1 minus f of xn minus 2 plus blah blah blah. And finally we get to f of x1 minus f of x naught, which is f of a. And that's going to be equal to the sum from 1 to n of f of xi minus f of xi minus 1. Okay? And all that stuff in the middle is going to be canceling out, so all we're left with is f of xn minus f of x naught, which is our f of b minus f of a. Okay, so this is our equation 1. We're going to use this a little bit in the proof here. Okay, now since big f of x is continuous, and why it's continuous is because it's an antiderivative. Because it's an antiderivative, that means I can take the derivative of that, and differentiability implies continuity. So the f of x is continuous on each interval in the partition, the xi minus 1. So it's differentiable on certainly on the open interval, and then continuous on the closed interval. So that is what we need for the mean value the mean value theorem. And so the mean value theorem says that there exists a CI in each of these intervals in our partition such that the derivative, or the slope of the tangent line at that particular point, and remember, because f is an antiderivative, when I take the derivative, and I'm talking about big F, so when we take the derivative of big F, it is little f. Okay, so each one of these Ci's is going to be equal to the slope of the secant line connecting the 2 points in my interval. Okay, and so what we're going to do is we're going to multiply both sides by xi minus 1, and for convenience we're going to call that delta xi, which is just the width of the interval. Okay, and so what this is going to do for us now is it gets it in terms of the original function f, and we'll say that's kind of our 2. And so the f of b minus f of a, remember that was in that formula 1 on the previous slide, it was that sum of the difference of the f of xi minus f of xi minus 1. So this is going to be the sum, I equals 1 to n, but we're going to substitute f of ci times delta xi. And again, we got that f of ci from the mean value theorem. Okay, this right here is that's a Riemann sum. Okay, and so f of b minus f of a, that's just a constant number, that's equal to this Riemann sum here. And the norm of the partition, we're going to let that go to 0. And the norm of the partition just means that all those delta xi's are going to get as small as we want, which means the width of our rectangles are going to get as small as we want, which means that we'll have a very good approximation of the area. Okay, so we're going to assume that the norm of the partition goes to 0. So f of b minus f of a. So when we let the norm of the partition go to 0, that's defined to be the definite integral from a to b, f of x dx. And that is QED for your fundamental theorem of calculus. We'll do a couple examples of it. So let's see what we got here. We're going to go from 0 to 3 of x squared dx. Now, if you watched a previous video, we went through and we found the lower and the upper sums for this particular function x squared between 0 and 3. We divided it up into fifths, and we went ahead and found that those lower and upper sums, and that gave us something that 9 was in between. Then we did it generically, and we took the limit, and we saw that both the lower and the upper sum converged to 9. So when I use this kind of, I guess it's kind of a shortcut comparison to the Riemann sum, is we're going to take the antiderivative of x squared, which is we add 1 to the exponent and divide by the exponent. So dividing by 3 is the same thing as multiplying by 3. And we're going to evaluate it at our endpoints. So we'll have 1/3, 3 to the third, which is 1/3 of 27, which is 9. And that's exactly the same thing we did when we took the limit of the lower and the upper sums in the previous video. Okay, I'm going to do two other examples. Here we'll take the one period of the sine function, and so 1 period of the sine function here is, we'll have the first half of it's going to be above the x-axis, so we'll have a quote-unquote positive area, and then the second part from pi to 2 pi will be a quote-unquote negative area because it's below the x-axis. So the net change here is going to be a 0 here. So we're going to go ahead and take the antiderivative. So the antiderivative of the sine is minus cosine x, and then we're going to evaluate it from our limits from 0 to 2 pi. Alright, so it's negative cosine evaluated at 2 pi minus negative cosine evaluated at 0. Okay, so here this will end up being -1, and this will be minus -1, because the cosine of 2 pi and 0 are both the same thing, which is going to give us a net of 0. Now, if I wanted to find the absolute value of the area, or I mean the absolute value of sine x, I'd have to divide it up into two pieces. So we're going to take a look at the antiderivative from 0 to 2 pi of the sine x dx. And so your sine function looks kind of something like this, more or less right there, and then this point here at pi is where it changes from a positive to a negative in terms of the function value. So we need to split that up. So what the absolute value is going to do is it's going to pop this portion up like that, so we have some two areas that we'll find here and here. Okay, so we need to split it up into two pieces. So when I'm between 0 and pi, I can just drop the parentheses. The sine of x is positive, and that's in quadrants 1 and 2. Now when I'm in quadrants 3 and 4, that's between pi and 2 pi, the sign is negative. So to compensate from that, because I'm doing the absolute value, I'm going to introduce a negative. So because the sign is negative, if I stick a negative in front of it, it'll make it positive. Okay? And antiderivative of sine is negative cosine, and we're going to evaluate that between 0 and pi. And the antiderivative of minus sine is cosine, and we're going to evaluate that from pi to 2 pi, and we'll just do each part separately. So negative cosine of pi minus negative cosine of 0 plus cosine of 2 pi and minus cosine of pi. Okay, and that's going to end up being 4. So when we do negative cosine of pi, that's going to be 1 because it's a negative times a negative times -1. And then we got negative and negative. Cosine of 0 is 1. Cosine of 2 pi is 1. And we have minus cosine of pi is negative 1. So we have 1, 2, 3, 4. That's 4. So that's our area there.